Hello. So the lecture I'm giving now is going to hit on a couple of things in section 3.3. We've actually discussed a lot of 3.3 already, but there's a few extra pieces I want to point out to you. And then we'll also deal with 3.4, which is about the complex numbers. The lecture on Wednesday included some talk about complex numbers, but there's a good bit more to be said there. So let's get going. The first thing I want to point out is a pretty standard way of referring to the parts of a sort of generic polynomial. The, you can see it in this theorem 3.8, which it's titled Cauchy's bound. It's this piece right here that I'm highlighting. I'm going to write it on paper and just go through bits of it. It's a little bit unusual. This book writes f of x for a polynomial. More often than not, people will say p of x if they mean a polynomial. But the rest of that line is pretty standard. The coefficients of the various terms are a letter. A is one of the first choices you might make with subscripts on them. So a sub n is going to be multiplied by x to the n power, and then the next one down would be a with a subscript n minus 1, and that's multiplied times x to the n minus 1. And that will continue all the way down to, well, the next to last thing would be a sub 1, which is just times x, and the last thing would be a sub 0. Now, in practice, in a real polynomial, you'll have the option that some of those a's might be 0. And so you may not see every term like this. But as an example of this, suppose I had the polynomial x to the fifth minus x cubed plus x minus 1, just as an example. Then what I've got in that guy is that a5 is 1, a4 is 0, because there is no x to the fourth term. A3 is minus 1. A2 is also 0. A1 is 1, and A0 is minus 1. The highest numbered A and the lowest numbered A have special names. This A5 and this A0 would respectively be called the leading coefficient. I'm just going to abbreviate coefficient because that's a lot to write out. Leading coefficient, and A0 is the constant term, or the constant. Actually, you can just say the constant or constant coefficient if you like. Okay, so I don't know why I felt it necessary to write that stuff, because it is sitting here in front of us in the book. Now, you saw from the last lecture one of the tricks we do to find the factorization, which is really about finding the zeros of a polynomial, is to just graph it and look for some of the zeros. And this first theorem, 3.8, Cauchy's bound, is giving us a sort of limitations on where we need to look. You don't have to worry about zeros showing up way off down the end or either end of the real line. The Cauchy's bound tells you, in fact, you can find a pretty small region where you search for the zeros. It'll always be in between two numbers. So what is this bound? You see how they've written a bunch of fractions. Well, I can't highlight things properly. Like here's a0 over a sub n, both of them in absolute values. A1 over an, again, absolute value of those things. That's a whole bunch of numbers. Basically, you're saying take each of the coefficients and divide by that leading coefficient, a sub n, or absolute values of these things. Then you're going to get a bunch of numbers. One of them is the biggest, right? That's the basic idea. M is the largest of the fractions you build like this. And then, actually not M itself, but M plus 1. It's possible that you get slightly bigger than M. Well, this interval between the negative of M plus 1 and M plus 1 itself, that's where you look for the zeros. It can be proved. I'm not going to go over it, and they squeeze a lot of it in the book too. It's a hard proof, which is why they're not wanting to show it, and why I don't want to show it. But it can be proved. There is a rigorous argument that any real zero is going to fall between these two numbers. Cool. They give an example here, but how hard is this? Let me just look at the basic outline of that polynomial. The leading coefficient is a 2, and then the biggest in absolute values of the other coefficients is this minus 6. So 6 over 2. The m is 3, that ratio we just got, and then we use m plus 1 or 4. You see how they came up with that? The interval from minus 4 to 4 is where you look for the zeros. This the next piece that there's actually 4 different theoretical results they're giving in this section. These two, I find, are practically speaking the ones that are of use in doing a factorization. The other ones are there, and they can be used, but they're less frequently necessary. So we're not going to bother with those other two. So we're doing 3.8 and 3.9. There's 3.10 and 3.11 also in this section, which we're going to just let slide. So, but these two, I believe they're both quite useful. So this is this next one, rational zeros theorem, usually called the rational roots theorem. It says something about any zeros that happen to be rational numbers. In other words, they're fractions. It says nothing about any zeros that are not rational numbers, like square root of 2 or square root of 6. These numbers that have no nice pattern in their decimal expansions, they're not rationals. Those things are on their own. But if you get a rational zero, you've got a limited number of possibilities for what to look at. So let's read this thing. It's got the same setup as the one before. F of x is this sort of standard notation for the parts of the polynomial. An, x to the n, etc. So its degree is n, right? A0 through an are all integers. So this theorem is not applicable if those coefficients are not integers. It's interesting to note, because there's, the examples that I give, or that any that we'll do in homework, normally have whole numbers, integers, as the coefficients, but they needn't. They could have, weird-looking decimals in there, or fractions, or square root of 6 as a coefficient. Why not? But in this case, we're looking at cases where all the coefficients are integers. So if you've got a rational zero, then R looks like plus or minus P over Q. That's true. That's what a rational number looks like. But there's more to this. It says P, the numerator, is a factor of the constant term. That is the number A0 at the end there. And Q, that'll be a factor of the leading term, or the leading coefficient, I should say. So that's kind of interesting. It limits the possibilities for what rational zeros there might be. I think they go through a nice example of this. First, they do an argument about why it's true, which I think we'll skip. But here you go. Here's a polynomial, 2x to the fourth, 4x cubed, minus x squared, minus 6x, minus 3. The leading coefficient is 2, and the trailing coefficient is, or the constant term, is minus 3. So what are all the possible factors of 2 and of 3? The minus isn't really going to enter into it, because we already are going to do a plus or minus in the rational zeros theorem. Well, they're not that many, right? Because both of those numbers are primes. So a factor of 2 is either 1 or 2, and a factor of 3 is either 1 or 3. So what we've got here, you'll see the final listings they've done. Why have they done it in twice? Oh, I see, just reorganizing things. Let's look at this first set of values, possible zeros, plus or minus. Well, the numbers in the tops are either going to be 1 or 3, and the numbers in the bottom are going to be 1 or 2. So this first pair of things has 1s in the top, and then one has a 1 and the other has a 2 in the bottom. The second pair of things has 3s in the top, and so then it also has to have a 1 and as well as a 2 in the bottom. So that gives us a total of 4 numbers. There's plus or minus signs in there, so it actually is a total of 8 numbers. So if you needed to do this kind of work without a graphing calculator or without Desmos, you'd come down to 8 numbers that you could use as the potential things to divide, well, to try to divide out a zero. And that's the whole story. Those rational zeros look like factors from the numerator divided by factors from the denominator. Said that wrong. The denominator consists of factors of the leading coefficient, and the numerator consists of factors of the constant term. Cool. For those wishing to use a graphing calculator, well, I normally like to take that approach. Use a graphing calculator. Use the technology if you've got it. I already did some examples of doing that in class. There's also in here a section whose subtitle is for those not wishing to use a graphing calculator. And this is, well, in our modern day, it's unnecessary. But you have to recognize that a lot of the tools that we use come from ancient history. Descartes lived in like the 1600s. So they didn't have graphing calculators. They didn't have anything approaching a computer, right? It was fairly primitive. In fact, in that period of time, if you used the word computer, people thought you were talking about a human being who was able to compute things well. Yeah, so in order to work without the technology that we currently are used to having, you need these other bits. Again, we're not going to talk about them at all, but I just want you to know the names. There's Descartes' rule of signs, which is about how you look through the coefficients of a polynomial and check how often does the sign of the coefficients change. Like this particular polynomial that they're working with, and they're going to do it without a calculator, has a +2, then a +4, then a -1, then a -6, then a -3. The changes happen right there between the +4 and the -1. There's one change in sign there. So it turns out that fact that there's just one change of sign tells you how many possibilities there can be for positive zeros. In fact, it's 1 or numbers that are smaller than 0, so they don't even make sense. So this polynomial can only have a single positive 0. I said I wasn't going to go through this, and now I've started going through it, so I'm going to stop myself. But that's the idea. There's some playing around you can do with seeing where the coefficients change signs, how often they change signs, and that will give you limits on where the positive and the negative zeros are. That's fun and everything, but not really necessary most of the time. There are also upper and lower bounds that are sharper than what we got from Cauchy's rule. So possibilities for the locations of the zeros we can be more exact about that. Not necessary most of the time. Cauchy's rule gets us a pretty good range to look into. So one thing that they do not do in this section, which they should have, is have you think about some special cases that are easy to deal with. So that is something I want to hit you with here. Let's not just write down in the bottom corner. Put that out here. these special cases are kind of important, more so in terms of, test questions and things on quizzes than they are in terms of, uh, you know, things that might show up in the real world. But we are going to get quizzed on this kind of stuff, so why not? All right, so what special cases do I have in mind? Often 0 is a 0, right? And in that case, what does it say about the factorization of the polynomial? Well, if 0 is a 0, that means x minus 0, which is just the same thing as x, that's a factor. So while I might have a polynomial of degree like 4 or 5 and 6, if it's got the right shape, you just go, well, there's a whole bunch of 0 factors or x factors that we can peel off. So let me give you an example of this. Suppose we had x to the 4th plus 5x cubed plus 6x squared. That was the polynomial. You very quickly look at this and go, oh, gee, every term has an x in it. So you can factor. In fact, you can factor out x twice. You can factor out an x squared from this thing. So this guy is x squared times x squared plus 5x plus 6. And that guy factors pretty quickly too. So we've got a total factorization of x squared times x plus 2 times x plus 3. And that means the zeros can be listed real quick because we had a whole lot of things that were just x's that we could peel out. We got through this rather rapidly. 0 happens with multiplicity 2. And then minus 2, that has multiplicity 1, and minus 3, also minus 1, multiplicity 1. So if you were to think about actually, we should just do this. I haven't got a Desmos window open, but it takes a second. It seems like more than a second. Did I not start the Chrome? Oh, there we go. Why is this so slow? This is my fast computer we're working on here. I don't know. What is this? Oh man, we're expecting more snow, huh? Great. Well, this probably won't affect us on Friday, which is what we're doing right here. Anyway, what do I want to do now? I want to show you Desmos, so I've got a bookmark for it. Let's plot that thing. It was x to the 4th plus 5x to the 3rd plus 6x squared. Yeah, so you should see the graph verifies the stuff we just figured out over here. We had zeros at 0 with multiplicity 2. You can tell that's multiplicity 2 because if you zoom way in on that, it pretty much just looks like you got a parabola. So it looks like y equals x squared. In fact, literally y equals x squared because this is happening at x equals 0. So that's the way a multiplicity 2 0 looks. We also have zeros at minus 2. There it is. And that's a regular multiplicity 1, 0. And at minus 3. Those are the numbers we got, and they just fall out of the factorization. So that's one of the special cases where 0 is a 0. Another special case, it's hard to sort of put a name to it, but it happens sometimes that you can factor by cleverly making a change of variables. I think in this case, I'm just gonna give you an example, and you'll see where the change of variables idea happens. Suppose we had x to the fourth power minus x squared minus 6. That is, well, it's degree 4, so, well, not so obvious. I could try to figure out where it might have zeros using the tools we talked about, like the rational roots theorem. The leading term is 1, so that's nice. The ending term is 6. The constant, rather, is 6. And the factors of 6 are 1, 2, 3, and 6. So we might have zeros at plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. Those are places where we could find the zeros. But I don't want to do that because there's a more direct route to this, which is to notice that, for instance, we've only got even powers. You can make a change of variables. I'm going to use y for the thing. So y equals x squared. Let y equals x squared. Now re-express this whole thing in terms of y. X to the fourth is x squared squared, so that's y squared. And then that's just y, and minus 6 is still minus 6. Can you factor that? Okay, change it back. Think about it as x's if you like. X squared minus x minus 6. Yeah, we've got a positive number times a negative number whose product is 6, and the difference is, or the sum is 1, but it'll be the difference because I know one of them is plus. Well, yeah, I guess it's pretty easy to factor that, isn't it? That'll be y minus 3 times y plus 2. So if this thing is supposed to be 0, that thing will be 0, and that means y minus 3 is 0, or y plus 2 is 0. Sorry, I've really run out of space on that little sheet of paper. Let me get a fresh one. All right, so that factor, let's just get rid of the substitution I created now. Remember, this is y was x squared, so what we've got is x squared minus 3 equals 0, or x squared plus 2 equals 0. Both of these lead to issues. This one, not so bad. If x squared minus 3 equals 0, then adding 3 to both sides, you get that x squared is equal to 3. And so x must be the square root of 3. Not quite right. I should say plus or minus the square root of 3. Yeah. If I work with that one, x squared plus 2 equals 0, I get that x squared is equal to minus 2, and I can't do anything with that, can I? Because there is no such thing as square rooting negative numbers. Well, for the moment, there isn't. If we're dealing with real solutions, there aren't any there. And you see now that stuff I was talking about, the rational roots theorem, doesn't apply, because if there were rational zeros that would have the form I talked about, there aren't any. This factor produces no zeros, and it's called an irreducible quadratic, and this one actually produces two numbers, but they're both irrational, plus and minus root 3. If we come back to Desmos and take a look at that graph, it was x to the fourth minus x to the second plus, no, minus 6, sorry. Very typical shape for a quartic, or x to the fourth thing, kind of a W in there. But you see the only zeros we're getting are there and there. And 1.732 is a pretty good approximation to square root of 3. plus and minus. Yay. Okay, so those are two special cases to watch out for, that you basically can pull out a whole bunch of x's, or that you can do a clever change of variables, reducing the degree down to something that's manageable by change of variables, solving it there, and then undoing that substitution that change of variables you've just done in order to get to your final answers in terms of the original variable. Okay, so then that is everything I wanted to cover in 3.3. Let's talk about 3.4. It really, 3.4 comes down to this issue that I was just describing here, where we need to take square roots of negatives. Complex numbers arise by saying, hey, why not? Why don't we pretend we could take square roots of negatives? That is a funny way to write it, complexes. That is actually how people refer to it, but I think I prefer to say complex numbers. These are things that have the following form. They look like a plus bi, where, what's the deal here? A and b are real numbers, and I has this property. It's the square root of minus 1. A and b are in the reals, and people usually write I is equal to the square root of minus 1. I prefer to say what I squared is. I squared would be negative 1. So you can write I equals square root of minus 1, or this, that amounts to the same thing. Yeah, so one thing you want to watch for is that only tells you how to take the square root of negative 1. Just call it I. But what if I have to take the square root of, say, negative 4? Well, it turns out to not be too bad, because square roots are just a power, and powers distribute over products, which means you can break that minus 4 apart into a minus 1 and a 4. And so you get an I and a 2. Wait, there was a plus or minus bit in there. Yeah. So I guess that's plus or minus 2. I is really just, we usually just say there's one square root of minus 1. It's I, although it's true that negative I is also a square root of minus 1. Anyway, I usually just do the work and then throw the plus or minus out front. Also, just by convention, this has no real meaning to it, but people usually put the I on the end and put the number up front. So this would be written as plus or minus 2i. All right, so if you have a complex number, it's going to look like this: a real number plus a real number times I. Yeah. Either one of those real numbers could be 0. So what do you get if, for instance, a equals 0? Well, then you're just going to have something like bi. In other words, this is called a pure imaginary number because it has no real part. It just has something that's multiplied times I. If b was 0, really at the bottom of the page here, then your guy is just going to look like a. And we don't say a pure real quantity, although I suppose you could. We just say real. So just really to make this point strongly, the real numbers are also complex numbers. They just happen to have a 0 as the imaginary part, as the thing that multiplies I. The pure imaginary numbers, things that just look like a multiple of I, those are a special case of complex numbers. Yeah, the reals are contained in the complexes. All right, well, we'll have to be able to, I need to be able to show you that these things are useful in the sense that you can do algebra with them, you can do arithmetic with them, and indeed they are in that sense. In fact, it used to be the case that people's attitude towards the complex numbers was this. If you, in the course of doing a computation, you ended up with complex numbers, you were supposed to just go ahead and play along with it, so to speak. Just pretend everything was cool. Keep calculating. But if you didn't get a real number in the end, if somehow those complex numbers didn't wash out and you ended up with something real, you didn't report an answer at all. That is, the complex numbers were thought of as kind of a means to an end. And if you didn't reach a real end, it meant that all that complex stuff was wasted work. Now we know, in fact, complex numbers are just as real as regular numbers are. They measure things that have, well, a little more complexity to them. In particular, if you do electronics, you use complex numbers all the time for the what's called the gain or the reduction in an amplifier, for instance. Things that have to do with varying electrical circuits, the kind of circuits that are called AC. If you know anything about that sort of stuff, the potentials in those are not just a certain number. You don't just say this many volts. In fact, you use a complex number to describe them. So electrical engineers use complex numbers all the time, and believe me, the stuff that they create with that is got concrete meaning. It's in higher math, complex numbers are used all the time. But for right now, the stage you're at in math, and mostly with an eye to sort of thinking about where you want to go, you want to get yourself ready for taking calculus. We're not going to see complex numbers until after calculus, probably. There are a few spots where it may be useful to throw them in, but for the most part, calculus is about real variables, and so we'll only have this one touch on the complex numbers. Nevertheless, I want you to know how to operate with them, how to work with them if you need to. And the first step in that is how to add and subtract them. So how do you add two complex numbers? Well, first off, I'm going to have to write down two complex numbers. One would be a plus bi. I'm just going to need different letters for the real and imaginary parts of the other guy. So C and DI, I guess. Here's how you add. You take the parts that don't have an I in them and add those. And then you take the parts that do have an I in them and you add those. And both of those had an I on them, so it sort of looks like you could factor the I out of those guys. That's a pretty simple way to do addition. It's almost what, could you imagine some other rule for adding these things? Turns out this has a very geometric character to it. And if you at some point learn about vectors, what we're doing is vector addition here. Okay, so adding isn't too hard. Subtracting is just adding the negative. So if you know how to subtract it, basically if I take that plus right there and put a minus in there, I could figure out how to do subtracting. All right, I guess I should do it. A plus bi minus c plus di. That would be a minus c plus b minus d times I. Okay. I feel like that's cheating. Or it's cheap to do that one, but it makes me feel like I've done more work than I have. How about multiplying? Suppose I take these two complex numbers we've been playing with, working generically here with complex numbers, and what am I doing? C plus D. And I want to take a product of those guys, multiply them. Well, does that look like a binomial times a binomial to you? Yeah. Except instead of, I guess if I were x, it would look exactly like two linear functions multiplied together. So that's the way you should think about it. Just FOIL rule, right? Except I personally like to not FOIL rule, but Floy rule when we're doing this. Just bear with me for a second. We're just going to do it in this order. First times first, then last times last. then outer times outer, and then inner times inner. Okay. So what's first times first? That's A times C. And last times last, that's BI times DI. Uh-huh. Okay, let's get the rest of it. Outer would be A times DI, and inner would be BI times C. Well, I'm going to rearrange that as BCI. So far, it looks a little ugly, but let me point out something to you. This term here has two i's in it, and I times I is I squared. That's minus 1. So you can re-express that as the negative of BD. And the other thing you should notice is that each of these guys has a single I in it, which you could sort of factor out and write that as AD plus BC all times I, which is pretty compact. Maybe I should do an actual example instead of working generically like that. So I guess I'll give you a nice one. 1 plus 3i times 2 minus I. This, again, Floyd. 1 times 2 is 2. Last times last is going to be, what is that going to be? It'll be the I squared, which is minus 1. There's another minus sign from this minus that's in front of the I. So we get a minus sign from the I squared and a minus from that thing. 2 minus signs, they go away. 3 times 1. Okay, so that's really plus 3. And outer times outer, that's minus I. And inner times inner is 6i. So both of those together have an I on. Well, that's interesting. It's 5 plus 5i. Kind of a neat, nice simplification there, isn't it? 6 and minus 1, 5. 2 and 3, 5. Yeah. That's right. Okay. Here's a funny one. I just want to show you one more example of this kind of stuff. Suppose I did like 2 plus I times 2 minus I. The Floyd rule of that would be 2 times 2 is 4. We just saw one where we had a plus and a minus term. So the I squared gets us a minus sign, but there's also another minus sign there. That ends up being just a plus 1. And then look what happens with outer times outer and inner times inner. One of them is minus 2i, the other is plus 2i. So really those guys are gone. So this product is 5, which I think is a little surprising. The product of two complex numbers ended up being a real number. Well, don't forget the real numbers are complex numbers too. So, all right. So that's fine. When does that happen? When is it that you get a number times a complex number times another complex number and it ends up being real? It happens in one particular situation, and it's the kind of thing you're looking at here, where the numbers in the two complex numbers involve the same the same real. See how there's 2 and 2, and the same imaginary things. That's called being a conjugate. So these things are conjugates of one another. If you want to be a little more accurate, you say complex conjugates. And complex conjugates are indicated by putting a bar over a complex number. So if I have a plus bi, and I put a bar over that, it means a minus bi. Just if there's a plus sign, replace it with a minus sign. Although similarly, if I take a minus bi and put a bar over that, that'll be a plus bi. which is kind of interesting. It gives you a rule that you can use. A plus bi conjugated twice is a plus bi. That is, if you do the conjugate twice in a row to something, you just come back to where you started. We're going to use complex conjugates and the fact that the product of complex conjugates comes out real to allow us to do division. So I've used up all the paper. Let's see if I can get a fresh sheet. This is a big sheet of paper, so now I'm going to have to be careful to stay in the bounds of my camera's view. Hopefully. And you won't be able to yell at me if I go outside. How am I going to do this? I'm going to make a little mark down here. There we go. So if I stay inside of that and don't move the paper, we should be all good. Yeah. So what was I saying? We gotta figure out how to do division. We're going to do division. So think about a complex number divided by some other complex number. It'd be great if we could simplify that. And you can. What you're going to do is multiply this by 1 in a kind of a funny way. You're going to take the fraction we've got there, a plus bi over c plus di, and times it by the conjugate of this bottom over itself. You see how that's 1? Well, now, the product I'm going to do in the top of these, the product of these two fractions, that'll be just the same multiplication of complex numbers we did before. And the bottom will be the the multiplication of a complex number and its conjugate. So the bottom will turn out to be a real number. That's a cool trick. So you will get, let's see, AC plus BD plus, what's the outer times outer, AD or minus AD plus VC pi, all divided by, what is that product of a number and its conjugate going to be? It turns out to be, in this case, first times first survives, so you get C squared. And then there's a single minus sign there, and there's a minus sign that comes from the two i's. That makes it plus D squared. Anyway, that guy's real, which means I went off the edge of the page. There's an I right there. That guy being real means we can kind of distribute that dividing by that into those things. So I've done it generically. I think it's more compelling when we do it, with actual numbers. I'm going to give you an example with actual numbers in it. Suppose I had the complex number 1 plus I, and I want to divide it by the complex number 2 minus I. I'll multiply by 1 in the form of this guy over its conjugate. Just said that wrong. Let me write down what it is. It's the conjugate of this guy divided by itself. That is also the conjugate of that guy. All right, so that clever way to multiply by 1 creates something that we can calculate. We'll get, what's in the bottom? 2 times 2 is 4, and then plus 1, or 5. And in the top, first times first is 2, last times last is minus 1, outer times outer is 1i, and inner times inner is 2i, so that's a total of 3i. So wait a minute, this is, whoops, don't want to work there. This is 1 plus 3i over 5. And if you really want to break this down till it looks like a real number plus a real number times I, just think about dividing both of those by 5. 1/5 plus 3/5 I. So look, these guys, these complex numbers are a little tougher to deal with, but not much. Honestly, not much. You have to FOIL rule to get the products. You have to do this trick with the multiplying by 1 in a funny way to do division. Adding was pretty simple. Subtracting almost as simple. Anyway, you can do all the algebraic manipulations with complex numbers that you can do with regular numbers. And that means you could, in principle, replace everything with nothing but complex numbers in every slot. We're not going to do that, but it's conceivable one could. Another place where this business of complex conjugates shows up is the quadratic formula. How does that work again? It's, let's see, the negative of b plus or minus the square root b squared minus 4ac all over 2a. If it happens that b squared minus 4ac is negative, then you're going to get a complex number out of this. But what you will get is negative b over 2a plus or minus the square root of some negative thing over 2a. And what does that mean? You're going to have a real part plus or minus the same thing. So the two solutions you get out of the quadratic formula, those are complex conjugates. It says something kind of interesting when you think about what happens with general polynomials. You've probably heard previously that a polynomial factors either into linear bits or these irreducible quadratics. I know you've heard it because I said it. Those irreducible quadratics, actually, they correspond to a pair of complex conjugate solutions. So when you get complex roots, they always come in conjugate pairs, and they correspond to these irreducibles that you sort of need to go to the quadratic formula to try to solve. And it kind of looks bad for things because you get that negative under the square root. So it turns out that there is a nice way to sort of, over the complex numbers, think about all the zeros. If you have a real polynomial, the zeros come up in two kinds. You have real zeros, however many you like, and pairs of complex conjugate zeros. And if you get down to doing the zeros of a polynomial over the complex numbers like this, where you get pairs of complex conjugates, a really nice thing happens. Ordinarily, you can have sort of any number of zeros. There are some things you can say. For instance, if you've got an odd degree polynomial, it's got to have at least one real zero. But if you look over the complex numbers, what happens is it has exactly as many zeros as its degree. So degree n, I'm sorry, I should make this into a sentence. A degree n polynomial has n zeros. Okay, one other issue that may come up. If you have a real zero that occurs with multiplicity, you've got to count it with that multiplicity. But basically, this is right next to the being true. It's just, okay, I'll make it true. We'll just put in a parenthetical remark that says we need to count them with multiplicity. Oh, one last thing to do in this section. I wanted to show you, sort of lead you through a theorem on page 289. Where are we at? Little ways to go. Sorry. Uh, 88. Here it is, 89. Some properties of the complex conjugate. Now, in this table or this theorem right now, they're using single letters, and the convention is usually this: that you use letters from the end of the alphabet if you want to have variables that refer to complex numbers. But think of that z as being a plus bi, and w is c plus di. This first one we've actually seen. It says the conjugate. If you conjugate twice, you come back to where you started. Okay. Is this obvious that the conjugate of a number plus the conjugate of a different number is the same thing as add them up and take the conjugate of that? Yeah, that's not so crazy if you work through what all that means with actual a plus bi's and c plus di's. You'll see it. This might be a little tougher, but it says that basically this conjugation thing plays nicely with multiplying. That if you multiply and then take the conjugate, or take the conjugates and then multiply, you get the same answer. And if it works that way for multiplying, then it'll work that way for powers, at least for natural number powers. Think of this as just being multiplying over and over and over again. Instead of z and w, we just have z and z and z and z. So the multiplication rule sort of implies this one. And then this last thing, and this will also be the last thing I'll talk about in this lecture. If you've got a real number, conjugation is changing the imaginary part. If you've got a real number, the imaginary part is zero. So if you have a real number, its conjugate will be itself. This sentence says if and only if, which is kind of, well, actually, it's not all that hard to see. If you know the number's conjugate is itself, how big can the imaginary part be after all? Yeah, it has to be zero, doesn't it? And that means the number's real. Okay, so that's it for section 3.4 for now, and I'll see you Friday.